Welcome back to another demo as part of MicroSim Mother of All demo. In this demo, we're going to construct together the Ben Eater 8-bit computer. So Ben Eater is a YouTuber part of the Khan Academy, and he has developed a very primitive breadboard 8-bit computer to help students understand about computer architecture topics. So together, I would like to demystify and to build from a bottom-up perspective the 8-bit computer. So the ISA, the instruction set architecture, is called SAP, which stands for as simple as possible. So we have a wide range of ISAs, such as x86, RISC-V, NIOS-2, etc. And Ben Eater come up with this SAP architecture, which is ISA, which is very nice to learn about computer architecture topics. So it has mainly two registers, the A register as you can see, and the B register. So you can only load and store content from the A register, and the B register is like a helper register. You cannot directly explicitly call it. So it's an 8-bit processor. This means that it can process 8-bit instructions. So to execute an instruction, we have to provide 8 bits of an instruction. So more precisely, in these 8 bits, the first 4 bits, the first nibble, is referred as the opcode, which means that it will encode which operation are we going to perform. And the remaining 4 bits that remains, we can be used depending on the instruction as an address that we can use. For example, in this table we have the provided instructions, and we have the load A. We're having this opcode 0001. What does it mean? Is that given an instruction that starts with this opcode, it's going to load in the accumulator the value that is stored at the address following by the 4 other bits. So this means that as we have it is a 4-bit addressable between code. This means that we can only address 2 to the 4 different addresses. This means 16 bytes of values. So we can only compared to our gigabyte or terabyte machine that we can access easily on the cloud, we only have 16 bytes. And furthermore, it's a von Neumann architecture. This means that the code and the data that we are going to perform operation on is merged in the same address space. So yeah, that seems not like a lot, but we can still do much with this architecture. That's great. So let's go over the instruction that are provided by the architecture. So this is referred as the ABI, the Application Binary Interface, because like the programmers are going to call or to encode the instruction using this Application Binary Interface, and the computer architects are going to build their CPUs in having this contract between the programmer and the computer architects. That's great. So we have the load A, which is, as I said, it's going to load in the accumulator the address that is part of the second nibble of the instruction. We have the add instruction, which is going to first load the instruction, the memory region, which is described in the second part of the instruction, and then it's going to perform an addition with the content of the accumulator with A, and then store the value in the accumulator. We have the same for subtraction. Then we have two memory instruction. We have the store A, which is as contrast of the load A, is going to store the value of A in a specific memory region in RAM, and we have after this the load immediate. So the load immediate it's a bit modified load A, which is going to immediately load into the A register some value. So the 4 bits value that follows the opcode are going to get loaded into A. So this comes handy for programming, just to directly set values in registers. We don't have to, for example, directly like refer to a precise memory address. We can directly feed the values. But in contrast, the values are going to be smaller. They have to fit on 4 bits. So it's a trade-off between what you have to do. Then we have 3 important instructions. We have first the jump instruction. So jump instruction means that once you are processing instruction, for example, the first instruction, then the second one, when you hit a jump instruction, it says, okay, instead of continuing linearly executing your instructions, what you're going to do, you're going to jump directly to this instruction. You're going to branch directly. You don't have to continue executing the instructions. So a modified versions of this jump instruction is a jump, but conditional. It's conditional on some values, for example, on some flags. More specifically, you have the jump on carry. So, for example, if the ALU, the arithmetic and logic unit, has enabled the flag register, the carry register, the carry flag in the flag register, it's going to, and it's performed after this jump on carry. It's going to jump. If there's no carry flag that has been triggered, it will just ignore and continue the flow. The same on the go for the jump on 0. So if the ALU, for example, sets the 0 flag in the 0 flag, it will perform this jump on 0. That's great. So finally, we have this 2 little instruction, which are the out, which is just like a printf, which is going to say, okay, so now the value that is on the bus are going to be stored in the out register. And finally, you have the halt. So the halt, as its name suggests, is just to say, okay, we can stop the processor. Right. So I spent a little bit of time just to understand this ABI, because it's going to come handy right after this. So now let's dive in a bit into the schematics, and we're going to see how each of these individual components are getting built up from bottom up perspective. So the first part that we have that's very interesting are the A register, the A and the B register, and these values, as they suggest, are going to get fed into the ALU. So that's nice. Then you have another interesting part is the PC. The PC stands for program counter. So what does this mean is that it points with like a register that says, okay, now we have to execute the instruction that is at this address in the RAM. So that's nice. Then we have the memory where the content is stored, and we have this memory address register which says, okay, so we have to go to feed in the bus this address. And finally we have the instruction register, which is, for example, when we say, okay, let's feed in the instruction, which instruction are we executing currently. So yeah, it seems a bit abstract, but we're going to dive in right after this small example. And one last, I would say, crucial, important part of this processor is the control unit. So the control unit is responsible to say, as you can see, it's sending pins to all of the different components to say, okay, so for example, now the ALU, you have the permission to write on the bus. Now you, the instruction register, you can read the bus, etc. and etc. It's like the dirigent of an orchestra that says, all right, let's given this clock cycle, what should we be performed, and which part of or which little factory in this processor should be allowed to write on the bus or to read from the bus. So yeah, essentially that's what's happening in the big picture. Great, so I would like now to show you the little program that is getting executed on Ben each 8-bit computer. And as you can see, the first part of the line denotes in blue is like the address at which we are going to write. So it's a 0, and then we have a load A 14. This means that we load in A the content at the address 14, which is 28. Great. Then the second instruction is going to do an add 15. So the add 15 says that we're going to load in the B register the content at the address 14, and we're going to store, we're going to compute an add operation and store the value in the A register. So 28 plus 14 is 42. Then we need to communicate this information with the exterior world. So we have this out instruction. When we have this out, it's going to store in the out register, and we halt. So we halt, it just means, okay, we're done, we can stop, and the results are done. So as you can see, it's a von Neumann architecture, as we mix both code and data. Great. So let's get started with MicroSim. Alright. So as the first part of the processor, I would like to show you the register. So just to have a quick reminder of how does a register works. So register works is like a piece of memory, I would say. So it has some random content initially. Let me just reset. That's great. And what we do is that we can send some clocks sitting. So we have some clocks, nothing happens. Great. So I would like to just turn on this write enable, and then what is going to happen is going to store the value that is here inside the A register. So let me just put one rising edge, and done. We have this value that gets transmitted. That's wonderful. Now I can, for example, change this value, and at the next rising edge it's going to feed this value in the data out of the A register. Great. Now let me just remove this write enable, and once we have removed this write enable, if I change, for example, these values right here, it will not transmit this value out on the data out. So yeah, this is a register. Now that we have the register, we can also have a look at the code. So in Verilog, it's straightforward. As you can see, on reset, we have the data that should go to the data out, and if write is enabled, on the positive edge of the clock, we put the data into the data out. Yeah. So let me just stop this and move to the next building block of the processor. We then have our ALU. So the ALU stands for arithmetic and logic unit of the processor. Let me just move this like this. Wonderful. So we can support two operation, I would say, the add operation and the subtract operation. So the add says that if the ALU up is an add, then you perform an add on 8 plus 1, which means 9 bits, just to detect if you have an overflow. And so you feed this, and you put the results on 8 bits, and the last bit is the carry flag, so this extra bit. And if we have this expanded results, which the result is equal to 0, so we should raise the 0 flag. Great. So we have an A, B value as an input, an ALU operator, and the results, and the carry flag and 0 flag. Great. So let's do the small demo. Great. So there's some random values that are just stored. Let me just put this back to 0. Wonderful. So as you can see, we have 0 as a result, so the 0 flag is set. So let me just put, for example, 3 plus 1 is 4. That's great. So now let me put 1 plus 1, it's 4, and let me change the opcode. So for now we're sending 0 as opcode, which refers to an add. Now we can change and have subtract. Subtract is a 1, so let me just put a 1, and now we have 1 minus 1. Oh, that's 0. Great, so the 0 flag is working well. So now that we have this, we can check the carry flag if it's working. So in order to have a carry, what we can do is have a big number, maybe like this, and we remove another big number, I think. Oh yeah, sorry. So yeah, it's overflowing now. Now it's not overflowing. Now we overflow. and yeah, so if we do this, it's even an overflow on this. So yeah, exactly. So we have 0 plus this value, so we have a positive value. If we do this, we have a negative value, so it's a carry flag that it sets on. Great, wonderful. All right, so our next part is going to be the program counter. So the program counter, which is here, yay. So let's run this and reset. So the program counter can perform mainly 2 operations. You can either increase the value that is in program counter, or it can enforce a value in the program counter. So the program counter is, as the A register, just a simple register, and the controller, which is here, will allow the flow to feed into the data out if we have, for example, the PC in, and if we have instead the increase counter, it will just feed out the value inside the program counter, as you can see. So let's throw some clocks, and normally nothing should happen. Yay. Now I order, for example, to the program counter to do an increase in the program counter. So I'd like you to increase the program counter. So let's do that stuff, and yeah, as you can see, the program counter is now counting. Now I would like it to stop, some clocks, nothing happens. Now I would like to feed this value inside the program counter. So I say PC in, and yay, you have to, yeah, exactly, you have to enforce this value that is now. For example, if I do like this, clock, whoa, what is happening? Let me just reset. PC in, and some clocks. Okay, let me just stop this. Ah, yes, I know, I remember, because the program counter is addressing, as you can see here, 4 bits of data, and because the address of the address space of the RAM is 4 bits, so it's 4 bits addressable. So for example, when I changed this opcode, nothing was happening, normal. So for example, if I just want to do, for example, so let me just do a reset, and let me enforce these values. So let me increase, let me clock. So great, now it's increasing. Now instead of increasing, I would like to do a PC in. I have put a PC in. Great, let me just change this, PC in, let me remove these values, clock, and yeah, now instead of having this, we have an increase, and yeah, we are increasing. As you can see, we overflow at 4 bits. Great. Now that we have this, I would like to show you the ALU with the registers. So it's this one, I think. Yay. So we have the A to B registers, the ALU, and we have this output value that is happening here. Let me just send this, some resets. Great, so let me just clear out the garbage values, the random values. Let me enable the writes, and let me send a clock signal. Yay, so we have 0 plus 0 is 0. Wonderful. Now we would like to do 1 plus 2. Let me just put a clock, and we have 3. Now if I remove this and change these values and send some clock, nothing happens because I need to enable the A register. Let me enable this, I enable, and yay, we have this. Now if I want to change the opcode, I want to do 7 minus 1, it's going to be 6. Great. So yeah, that's what I have to show you for this small demo. So let's move on to the next one. Right. So the next one is going to be about the control or maybe not the RAM. The RAM is better. So the RAM is just to show you. So we have this memory address register here, and we have this RAM which is here. It's wonderful, and depending on the contents of the value of the memory address register, it will fill up the RAM. So this is how it works. And the control unit has these different pins, and depending on the internal step of the control unit, is going to enable one of these pins. Great. So let me just go back to my slides, and I think that I cover all of the different elements. That's nice. Oopsie. Great. So we're going to perform this little program that we have seen right here to just check if the architecture is working. So let's go back, and we're going to open the main 8-bit.MicroSim. So before, and now remember, before diving into the demo, I would like to show you the control units, because it's the most, like as I said, the heart of the processor, and I would like to show you. So we have this output flags, or I would say like pins that enable different parts of the processor, and we have this as input the instruction on 4 bits, like the first nibble. Then we have the clock, the resets, and we have as input if we got the carry flag or a 0 flag, then we can like output these values. So we have here the bus mapping of the different elements, and we have here the instruction encoding. For example, for a nope, no instruction, it's just 0. For the load immediate, 1, etc., as we have seen in this table. Then these values are the ALU operator. So if I just open ALU dot like this, we have this operator that are opcode that are here. Then we have this, I would say, an event loop. I don't know if we should call it like this, but it's like an event loop. So initially we reset everything. So the reset control is just puts everything to 0, and we select nothing. Then we go back to this event loop. We have the step counter which stays to 0, reset everything. Then if the step is equal to 1, then we also reset everything. Then if the cycle is equal to 1, we're going to perform the fetch cycle. So the fetch cycle, so the processor works into, it's like a multi-cycle processor, which is going to fetch, decode, and execute the instruction. So the fetch cycle is just in here, and it will say, okay, so in the bus selector, I'm interested into having the program counter. So for example, here is our bus, which is the value in the bus, and is like feeding in the backside all of the elements, even itself here. And I say I would like to be interested into having the value into the program counter, which is here. That's nice, and that's why I'm enabling this memory in value to say, okay, now this memory in value, which is mem in, to say, where is mem in? It's here. Sorry, it's about to be about this memory address register. Say memory, you have to go and to enable your value. Then we do the same for the program counter, I think. Oh no, it's just in memory. Yeah, we advance the program counter. So we say, okay, great. So now that we have this program counter, we're going to advance. So it's like inc program counter, which is right here. Advanced PC inc. That's great. So once we have performed our fetch cycle, we're ready. The instruction and the memory address register are loaded. Now we can, depending on the instruction, which is this 4 bits, we're going to perform the correct instruction. So it's like a switch case that, depending on this, is going to perform. So I'm going to show you, for example, the add, as I discussed a lot on this. So first you just say, okay, I would like to feed in the register B and to enable the flags in the value in the bus memory. So I say, okay, the register B, I'm interested into feeding your value. And then we perform an add as we put the value for the add ALU operator, and we store the value in the register A. As you can see, the register A would get write enabled from the bus value. Great. So yeah, so that's it. Essentially, that's how does the processor works. So now I would like to load the RAM. So the RAM is this value, and the RAM, okay, let's just remove this, and we need to program our RAM. So we can do it manually, but it's a bit tedious, as you might have guessed. So as for the Morse demo, I have created in here, let me just activate, and I have this pseudocode, not pseudocode actually, it's the add.is assembly, which is in the assembly, and it's exactly the same code as has been discussed in this video of Benature. So I discussed this a bit in the introduction, and now I would like to load this content into the RAM. So how do we do this? We cannot copy paste this, but almost. So I have this assemble program in Python, as I did before, and what it's going to do is, like, it's going to transfer, for example, if I have a nope, or for example if I have an add here, an add, I'm going like to concatenate the value of the add, which is 0010, and add this second value, which is here, for example 15, and we're going to put like an F, and that's essentially what's happening in this program. As you can see, I'm like having the address, and I put the opcode, I shift it by 4, and I put the low, and then I just write the content, and this is the template code I just have, and yeah, just writing this file. So I would like to show you this. I just need to do, so have a look at this region, and let me just check, let me go to cd ism, assemble, add.ism, bam, now the memory is loaded, and we have this value. Great. So we are ready to simulate our processor, and to do this I would just need to reset the values when it starts, and so that we can enable the processor. So let's press play, reset, and we should have so the processor has halted, as it was mentioned by the assembly, and we have 42 as the result of our instruction. So the clock was a bit fast. Yeah, I should make the clock a bit less faster to showcase what is happening. So now for our next demo, I have, let me check my ISM values. Yes, I do have this other program, which is subadd, which is a bit interesting, which is going to perform to load A, so it's going to load 5, then going to add with the value of 14, so it should be 11, then we should subtract with the content of 7, which would be 11 and minus 7, and then we put the results out in the out register, then we hold. So let me just again assemble this, and voila, we have it loaded in the memory. We can close this, and this time should just remove this. Great, let me press play, and we're going to reset and look at the signal analyzer, what is happening. Great, just pause this, open the signal analyzer, go here, and I'm interested in the values of the A register because it is the accumulator, and we shall see, yes, now let me format the values to decimal, and yay, what we have 5, then we have plus 6 is going to be 11, minus 7 is 4. Yeah, so let me just show back this assembly. Great, yeah. So yeah, 5, 11, and then 4. And as an out, we have this 4 that gets printed. Alright, so this is just some proofs that like the processor is working, but come on, let's do something more interesting. I would like, for example, to count the multiples of 3. So that's what I'm doing in this example right here. So it's an example that has been taken from Banicher again, this address. And essentially what it's going to say is that first we load immediate the value in the 8 register of 3. Then we store the content on the address 15. Then we load immediate to 0, and then we continue. So what is happening here is that we're going to loop indefinitely to print out the multiples of 3. So this is just an init, then we loop on here. So let me just assemble this program. Alright, it has been assembled. Now I can press play. Let's just reset. And normally we should see 3, 6, etc. Great. Another interesting part is to simulate or to execute Fibonacci, because Fibonacci is a sequence that is going to explode, and we need to handle this overflow. So as you remember before, I was talking to you about this jump on carry, so we're going to try to execute this. But we cannot just use it this way, as the 8-bit processor is a bit I would say limited, but in a sense we need to swing with these limits. So we have this pseudocode before, which we're going to transcribe into assembly. So first we perform the check that's of x plus the previous value, and we print this. And once we have printed it, we're going just to check if it doesn't overflow under its representation over 8-bit. So otherwise we cannot continue the computation. And if we do this, we come back to 0. So yeah, it will loop back. So the Fibonacci.ism is here. It's really taking back this pseudocode. I should put it here, and it's implementing it. So I modified the code that is in this video, because there's like a little bug in the architecture of Banicher that I patched to make it able to go till 233. Otherwise, it will, in Ben's demo, it goes I think till 140 something. So as you can see, there's this loop, and there's the init, which is here. The init is here, and the loop is here. And I'm going just to do a equal to y plus x and check the overflow, and put like the carry flag. I will jump to 0 if I have detect the carry flag, or otherwise if there's no overflow I can just go back to the loop. And for the 14 and the 15 values I'm storing the x and y values. So as you can see, I have been using 15 out of the 16 possible addresses in the RAM. So it's very interesting. With a limited address space, we can still perform Fibonacci. So that's great. Let's assemble this program, and let's see how does it performs. All right, Python assemble Fibonacci.ism. Enter. Yep, has been loaded right here, as you can see. And I would like just to run the simulation and to reset, please. And now let's focus on this value. 1, 2. So now the clock is not too fast. It's my program that is too slow. So let's have a look at this carry flag and 0 flag. Because 233 plus 144 is like exceeding this 255 bound, and now we're looking back, as we can see in this program. So yeah, that's Banicher's computer. it's running Fibonacci. So that's what I wanted to show you for the Ben Eater 8-bit computer. Let's stop this and let's go back to the slides. So in these settings, I just would like to do some ISA extension on live, because I can show you that this platform is very flexible and we can really do a lot of stuff with it. So the first ISA extension that I would like to do is the shift left logic and shift right logic. So what does it mean to shift? It just means that we are going to shift by 1 bit the content of the A register, and shift right logic is the same but in the other way around. So let me just let this open and open the ALU. And in the ALU I need to define 2 new operations. I need to define the shift left logic, which is going to be the next logical opcode, and the shift right logic, which is going to be this last opcode. Great. So now how do we say that we have this shift operator? So in Verilog, what we need to do is, so let me just copy paste this once, and instead of having this sub shift left logic, and what we do is just, so we don't need this, and we're going to perform a shift by 1. That's great. Now let me just copy paste this, and instead of having shift right, great. So now let's test this setting just to check if it works. So we have this test bench ALU. Great. So now let's press play. Let's just remove this random values. Let me put a 2 and let me put a shift. Great, so it has been shifting. And now let me put a shift right. Yeah, as you can see, it's shifting right. Great, so the shift is now working. So what do we still need to do? We still need to do is to enhance the control unit, because as I said, the control unit is like the dirigent of the orchestra of the processor, and it needs to inform the ALU to perform this operation. So what we can do, let me just close this, is go back here to Verilog. Great, and let me just copy the control unit into control2.verilog. Wonderful. Now that we have this, we should be able to have it here. So let me just, now this control unit is not obsolete, but it's not responds our needs. So we can just put it here, drag and shift it. Whoopsie. Yay. Let me just zoom in. Great. So now it's completely connected, but we still need to do some improvement. So let's open this control file, and what we first need to do is to import this new opcode. So here, let me just declare these 2 new opcodes. Then what we need to do is to create the instruction encoding. So let's take this and let's mark it as a 1. We can pick whatever we want, but just as matter to be consistent. So shift left logic and shift right logic. Minus, save. Great. So now what we need to do is, if we detect a shift left logic, we need to execute the actually relevant operation related to a shift left logic. So what we're going to do is, let's copy paste this instruction and say if we have like a shift left logic, we're going to perform shift left logic, and we do the same with the shift right logic. Great. So we're going to inspire ourselves from the add operation, because the add is quite similar. It's using the ALU, but adapt it for the shift left logic. So what we need to keep is this flags in. We can remove this second port as we don't need it. And what we need is indeed to perform not an add, but a shift left logic. Wonderful. That's what we have this. We can copy this task and perform a shift right logic. That's great. All right. So now our control is ready. What is not ready is the code. So the code that I propose to do, so let's go in here. And let's touch something which would be called ping pong. That's ASM. So why ping pong is because we're going to do some ping pong actually with the 8-bit processor. So let's open ping pong. Great. So what we're going to do is we're going to perform the following task. Is that we're going to first, how do I say? If we're in the first part of the loop, we're going to shift left. So we're going to first ping, and once we overflow, we're going to do the pong. So how does this materialize? So first, we should load immediate a 1 in A. So we init A to 1, right? Then, okay, we're going to just output it, just to say what is happening. Then we perform this shift left logic. Once we do this, we need to do as a 3 again out, just to see the difference. And finally, that's 4. If we have overflow, so we have need to go, so we need to loop while no overflow. Great. And if there's no overflow, we can confidently jump to 1 to say, okay, no overflow. So yeah, no overflow. Can continue. Then what we have is, if we have an overflow, so if we have an overflow, we have to go to 6. We don't have to perform this operation. Okay, great. All right. And if you have an overflow, what we need to do is just to go to the out register and to perform a shift right logic instead of a shift left logic. And we output it. And finally, we do the other jump conditional, which is a jump on 0. We go back to 0. We just need to initiate it back. Just put this. And otherwise, we just jump to 6. On underflow, no, sorry, this is underflow. This should go here. Underflow, we should init, and otherwise we can confidently continue shifting. All right, so once we have done this, let me just do a small modification to the processor. Let me change the encoding. Let me do a bit by bit so that we appreciate more the ping pong. And let's assemble this program in the RAM. Yes, there is an error because I just added an instruction and my assemble does not recognize this instruction. So we need to add this following instruction, which is if I have a shift left logic, I need to add this opcode. So I don't remember the opcode. Let me just go here. So it's 9. Okay, it's 9 and 10 for the SLL. Yay. Achieved right logic. It's 10. 10, 10. A. Great. Let me assemble this. Now it has assembled, as you can see. And we can, if everything works correctly, we should be able to run this. Alright. Moment of truth. Yay. We are shifting. Yay. Carry flag. And continue. Zero flag. We continue. Ping pong. Wonderful. That's amazing. Alright, so let's go back to the slides one more time. And for our next demo, I would like to do on live the Morse ISA section. As you remember from our last video, I talked about Morse, and now I would like to do some Morse ISA extension. Also, it's very useless as a processor, but it's fun to do it. So let's do this. So for the fun instruction, for the Morse instruction, what we need to do is actually go to the control units and add another flag, which is going to be, let me put it here. Yay, remove this comma. Let's name this Morse in. Okay. Then on the reset, we need to set this value to 0. So let's go back. Oops. So let's go back, and then what I can do, can directly put this to 0. And then what we need to do is have the instruction encoding for this instructions, for the Morse instructions. What we need to do is copy this. Let's name this instruction as Morse, and let's take, for just as the sake of purposes, the next one. Okay. Now what we need to do is to say, if we have the Morse instruction, let's perform a Morse instruction. So again, let's inspire ourselves from this add. And what we're going to do is we're going to play on Morse the value that is going to be stored in the A register. So let me just again inspire myself from this, and if we have finished our processing of this, we can just confidently put the step to 0. If not, what we need to do is, as a reminder, this Morse operator, this Morse player, needs to play for 16 instructions. So when we are here, we are at our second step, so we need to wait until the 18, 2 plus 16 is 18, and we need to say, okay, Morse entry, it should be enabled. Wonderful. And with this, we just need to change, the processor. We need to change the processor. Let me just remove this. And the processor, let me just put it back to decimal. Use it like this. And also, let's open back our Morse, which was here. Come on. Okay, let's go here and let's copy paste this element from one description, one MicroSim, to another, and let me just take the value of the A register, which is here, and feed it right into this. That's wonderful. Let me just, don't need the LED, actually connect this here. Okay, and now, yes, I need to connect this driver, which is the Morse in, with the controller. Great. So let me just take back my controller, control 2, shift. This is done. We don't need this anymore. Thank you for your service. Now we can map this value in the instruction, which is like the first nibble, as you can see, the first 4 bits. And we just need to add this channel to here. So this is yay. All right. So now what we need to do is program this machine. So how do we program this? We again go back to this assembly. We can touch, for example, morse.ism. And what we are going to do is, yay, please. Okay. So what we would like to do is first set the letters. As you might remember from these values, let me just put it, so we don't need this. Let me put the RAM. Yay. Here. Wonderful. And what we can do is this is first store the values inside that we want to play. So I like this SOS message because it's very straightforward. So let me just store, for example, the S, so S in here. Okay. And let me just put in the 15 address the O. Okay. Whoopsie. All right. So now what we need to do is very simply load in A. That's our first instruction. We need load in A the content at the 14th address. Then we need to perform this Morse operator. Morse. Okay. Then what we do, we should load A with the address 15. Whoopsie. And then we play again Morse. And finally, we can again load the S. And we have this, our last instruction is going to be a Morse. And as we don't want it to crash, can just perform as the 6th instruction, this address, the Morse. So from our last video, as a quick reminder, the S encoding in ASCII is 83, and the O is 79, I guess, 79. Okay. So that should be working. The last pinnacle point that we need to take attention is in our assembly program. So let me just take back our control units. And which encoding did we pick? Is 11. Okay, so B. Yay. 11 going to be this Morse instruction. That's great. So we can close this. We can close this. Put it like here, and very gently assemble this Morse. There might be an error. Let me check the Morse.asm. And the Morse.asm is complaining about don't see the error. Let me just open back this assemble. It's Morse. Okay. Ah yes, I think I got it. It's because I introduced a white space here. So let me just remove this white space and go back to the terminal and open the RAM if possible. Great, so we have it loaded. Now what we can do is to run this processor. So let's run this processor, and hopefully it will play SOS. Wonderful. Let's reset it once more to hear SOS. So we successfully did our ISO extension. Wonderful. Let's stop this and come back to the slides. And with this concludes our ISO extensions. I would like to thank you for your attention. I hope you enjoyed, as I enjoyed, doing these small demos. Thank you and see you next time.